What would happen if an interstellar object suddenly flared up directly facing the Sun and defying every law of physics? The object 3I Atlast, a visitor from beyond the solar system, is exhibiting a sudden rhythmic increase in brightness. This event is not merely an optical phenomenon, it is a scientific dialogue written in fire and plasma. Astrophysicists are racing to decode the signals from the aurora-like glows flickering across Atlast's surface to its astonishing synchronization with the strongest X-class solar storms of the decade. Let us embark on a journey to unravel the source of this radiant energy, to better understand the thin boundary between interstellar matter and the safety of human technological civilization. For several days, astronomers have watched an unexpected surge of light bloom from an interstellar traveller, ThreeI Atlast, now nearing its closest pass to the Sun. The rise in brightness is not subtle. It is sudden, deliberate, almost alive. Sensors from solar observatories record a steady escalation in magnitude, the glow doubling then tripling as Atlast enters the fierce corridor of solar radiation, where dust plasma and magnetic fields collide. What should have been a calm, predictable approach has become a storm of photons. ThreeI Atlast was first catalogued as a cold visitor, a relic drifting between stars, but recent frames from the C2 and C3 coronagraphs tell a different story. The object brightens against the black field, its reflective halo widening beyond all early models. Teams at NASA's Solar and Heliospheric Observatory measure the visual gain at more than one full magnitude beyond expectation. The European Space Agency's monitors confirm the anomaly, light curves rising steeply, energy output consistent with a major outgassing event or a reaction to solar wind compression. Each data line whispers the same pattern: something within Atlast is awakening under heat. Atlast now moves through a region only a fraction of an astronomical unit from the Sun, crossing the inner boundary of the corona, where the solar wind thickens into turbulent plasma. Ordinary comets release jets of vapor and dust when they reach this proximity, but Atlast behaves differently. The ejected material does not disperse evenly, it streams toward the Sun in a narrow arc, as if magnetically steered. Spectral analysis from ground-based stations in Chile shows a spike in ionized sodium and faint traces of carbon monoxide, but not the wide dust tail expected from water ice sublimation. This deviation fuels a rising conversation among astrophysicists about whether the composition of ThreeI Atlast could belong to a class of interstellar carbon-rich bodies never catalogued before. The Solar Dynamics Observatory records a flare at the same longitude as Atlast's trajectory. Some call it coincidence, others mark it as a possible interaction between the comet's ion cloud and the solar magnetic sheath. Within hours, magnetometers detect a pulse barely measurable, but synchronized with Atlast's passage across the inner corona. It is as if a silent handshake occurred between a star and its visitor. Researchers replay the data, seeking correlation, hunting for cause and consequence. So far, the instruments agree only on one fact: the brightness spike coincided precisely with a surge in solar activity unseen for decades. ThreeI Atlast becomes for a moment a mirror to the Sun's own heartbeat. Its surface, thought to be composed of dark interstellar minerals, now radiates with the pale shimmer of electrically excited gas. Models from the Harvard-Smithsonian Center for Astrophysics suggest that charged particles from the Sun could be funneling along the object's transient magnetic field, generating luminescent discharges across its surface, miniature auroras on an alien core. If true, Atlast would be demonstrating a process rarely observed outside controlled plasma experiments: magnetic reconnection on a subplanetary scale. The brightness curve plotted over the last 72 hours tells a story of acceleration. From magnitude +9 to nearly +6 in less than 3 days, an immense leap for a body at such distance. Scientists compare the pattern to previous interstellar objects, yet neither Oumuamua nor Borisov displayed anything similar. Atlast defies the expected curve, and the community watches the numbers with both wonder and unease. If the emission comes solely from reflective ice, the energy should plateau. Instead, it rises in pulses as if responding to solar rhythm. Within control rooms around the world, algorithms flag the event as an anomaly, but not an emergency. The public feed from coronagraph CCR1 displays a glowing arc around the Sun, a small bright knot at its edge, the mark of ThreeI Atlast. Commentators call it a spectacle. Astrophysicists call it a data point written in fire. For them, every frame is an opportunity to decode what interstellar matter becomes when confronted with the gravity and radiation of a living star. They know that this moment will never repeat in the same form. If Atlast's core contains volatile compounds locked since before the sun was born, the heat it now endures may be releasing gases untouched for billions of years. Each molecule escaping into space carries chemical memory from another system, another dawn. The brightening could therefore be both destruction and revelation, an ancient archive dissolving into light. Such an interpretation, though poetic, remains within the bounds of physics: sublimation, ionization, reflection, all amplified by geometry and time. Yet there lingers the possibility, faint but persistent, that Atlast's radiance is not purely reactive but communicative, its pattern too rhythmical, too exact. The bridge between data and meaning is thin. Astrophysicists resist metaphor, but the human mind seeks one. We look at the surge of light and sense intention, a pulse that echoes our own search for order. Perhaps Atlast, forged in a distant system, merely mirrors the chaos of the sun, or perhaps the sun itself answers a call we do not yet recognize. In the final readings from CCR1 and C3, the object gleams brighter than at any previous pass, its halo curling like a signal flare inside the solar wind. Telemetry continues to stream frame after frame as instruments fight the glare. Among the columns of figures, one truth endures. ThreeI Atlast has brightened dramatically, and in that surge of light a question unfolds: was this expected? Or are we witnessing a conversation written in radiation 1? We are only beginning to hear the sun is waking up. After years of quiet patterns, scientists have begun to witness an unmistakable rise in power, massive X-class flares lighting across the solar disk more intense than any in recent memory. 3. Atlast moves through this volatile corridor as if drawn into the storm's path, reflecting bursts of radiation that ripple outward in waves. Every reading suggests a star entering a phase of renewed turbulence, and Atlast has become the perfect mirror for its awakening. Solar observatories around the world, SDO Soho and the ground-based Gong network, are now recording regions of concentrated magnetism large enough to swallow Earth several times over. Those dark patches, called sunspots, rotate steadily toward the Earth-facing hemisphere. Each one carries twisted lines of magnetic energy straining for release. When they snap, the sun throws out titanic arcs of plasma, called coronal mass ejections, that travel at millions of kilometers per hour. 3 Atlast, already close to the perihelion, lies within that expanding web of energy. Its reflective profile brightens further under bombardment, turning into a transient gauge of solar aggression. Instruments at NOAA's Space Weather Prediction Center confirm multiple X-class events, one flare reaching a magnitude unseen since 2003. The GOES-18 satellite captures spikes of hard X-ray emission, while the Stereo spacecraft records shock fronts sweeping through the heliosphere. For comparison, an X1 flare is already powerful enough to disturb high-frequency radio communication on Earth. The most recent flares are 10 times that strength. As these storms intensify, 3 Atlast drifts through streams of charged particles capable of stripping surface materials into vapor. Every encounter writes new data into our understanding of both cometary physics and the volatile mood of our star. Astrophysicists monitor the timing between Atlast's brightening and solar eruptions. The alignment is uncanny. Flares ignite precisely as Atlast reaches new positions along its trajectory, as if the object were tracing the rhythm of the sun's heartbeat. Models from NASA's Heliophysics division simulate the solar wind density across the region and predict compressive waves that could double the impact of each flare. That means more pressure, more drag, and higher chances of geomagnetic consequences on Earth. The quiet auroras that once painted the poles could soon explode into color visible far beyond their normal latitudes. Observatories in Europe and Japan report massive coronal loops rising above the solar surface, shimmering arcs that extend hundreds of thousands of kilometers into space. 3. Atlas crosses beneath one of these arcs, vanishing briefly into its glare before reappearing brighter still. Its albedo increases sharply, almost as if the object were coated in an electrically conductive material responding to solar charge. Researchers describe the interaction as a dynamic feedback loop. Atlast reflects energy back toward the corona, slightly altering the particle flow in its vicinity. Such feedback is minor but scientifically unprecedented, suggesting that small bodies can momentarily participate in the sun's magnetic drama. The current solar cycle, once expected to be modest, now threatens to surpass forecasts by a wide margin. Cycle 25 shows a sunspot count exceeding models by nearly 40%. Every parameter, solar wind density, proton flux, X-ray output, points toward a system in agitation. 3. Atlast serves as an unintentional witness to this escalation. Wherever Atlast drifts, the sky trembles in data. Electron storms, proton surges, whispers of gamma emission. It is as if the visitor's presence amplifies what was already inevitable. Space weather teams prepare for a cascade of effects. Geomagnetic indices climb higher by the day. Satellites in low Earth orbit switch to protective mode, minimizing exposure to radiation spikes. A few have already reported anomalies, temporary signal loss, unexpected attitude shifts, data corruption that engineers attribute to solar interference. 3. Atlas glows fiercely under this onslaught, the color of molten gold in solar imagery, an emblem of both danger and discovery. The flare watchers compare notes, radio blackouts along the Pacific, voltage irregularities in long-distance power grids, GPS drift measured in fractions of seconds. Each symptom hints at the same source, the storm above us. The sun's surface seems to pulse like a living organism, inhaling plasma, exhaling fire. In laboratories, simulation clusters run continuously, predicting geomagnetic indices, tracing magnetic lines, like veins of an invisible body. And within that body, ThreeI Atlast continues to move, carrying the sun's reflection wherever it goes. The bridge between solar violence and terrestrial life narrows. Scientists warn that the next major coronal ejection could align directly with Earth's magnetic field, compressing it in hours. If that happens, satellite communication will falter, auroras will ignite over equatorial skies, and the fragile web of technology surrounding our planet will quiver. Power grids might flicker and fail. Communication systems could dissolve into noise. ThreeI Atlast, caught between gravity and radiation, reminds us how thin the boundary is between order and chaos. For now, the data flows steadily, a heartbeat of numbers echoing through observatories, all carrying the same caution. Extreme solar activity is not approaching, it has already begun. A black disk covers the sun. Behind it, the hidden violence of the corona becomes visible, great loops of plasma shining in temperatures that can melt metal and vaporize stone. The coronagraph stretches its vision 32 solar radii from the center, giving scientists an unobstructed view of what unfolds around the star. Through this shielded eye, the immense geometry of solar motion is revealed. Arcs of white fire lift, twist, and then break away from the sun in immense bursts known as coronal mass ejections. Each eruption carries billions of tons of charged particles through the solar wind, a storm that ThreeI Atlast must now navigate. ThreeI Atlast appears on the outer edge of the field, a small moving point against the radiant expanse. Its path cuts across a faint haze of plasma debris flung outward by a recent flare. Telemetry from SOHO and Stereo A confirms the trajectory, and instruments show the density wave traveling outward at speeds exceeding 2,000 kilometers per second. As this wave expands, it creates a halo of scattered particles that glows in ultraviolet. Atlast drifts through that halo, and for a brief moment its outline becomes sharper, as though the sunlight around it has turned liquid. Coronal mass ejections are not rare, but the scale of those seen in this cycle defies precedent. The solar disk is constantly reshaped by the emergence of magnetic loops that store and release energy, like the twisting of invisible springs. When these loops collide or reconnect, they hurl plasma into the void, each pulse a release of pent-up magnetic tension. ThreeI Atlast, crossing through the expanding shock front, acts as an accidental probe, its brightening surface recording every fluctuation of the electromagnetic sea. Observatories tracking the motion note how its reflected light flares slightly after each CME, as though responding to the shock itself. Data from the LASCO C3 instrument shows multiple fronts racing away from the sun, overlapping like ripples on a pond. In between the void pulses with ultraviolet radiation and particles of helium and carbon. The speed of the ejections varies from one to the next, but the direction remains consistent earthward. Astronomers begin to calculate arrival times for geomagnetic interaction, predicting a surge of auroras visible well beyond the polar zones. Atlas, caught within this stream, becomes a tracer particle in a storm of cosmic wind. The energy it absorbs will later translate into the luminous flare already visible in other instruments. The conversation between sun and space continues in light and plasma. Each eruption reshapes the heliospheric current sheet, that invisible membrane that defines the flow of solar wind. ThreeI Atlast crosses it at an angle, slipping between sectors of positive and negative polarity. The movement is delicate and dangerous. Any large flare at that moment could strip its surface of material entirely. Yet Atlas persists, reflecting the chaos in pulses of white and cyan. Ground observatories in Hawaii and Australia report synchronized brightening patterns, the signature of its crossing. Scientists working with the European Space Agency's solar orbiter watch these developments with a mix of awe and calculation. The instruments detect shock-driven waves in the solar wind compressions that rattle through the heliosphere. One of those waves reaches Atlast's projected position, and a sudden shift in its apparent brightness follows within minutes. It is a perfect coincidence of timing proof that Atlast now drifts through the heart of a living experiment, the interaction between starborn storms and interstellar matter. Every meter of its surface carries the scars of this dialogue: pitted minerals, faint halos of ionized gas, and the steady hum of energy transfer. On Earth, the effects are indirect but unmistakable. Space weather alerts begin to circulate quietly between observatories and power grid operators. The magnetic indices rise. Atmospheric models show the upper ionosphere beginning to swell as charged particles descend along magnetic lines. The auroral oval stretches, pushing light and color deeper into mid-latitudes. Meanwhile, in the glare of the coronagraph, ThreeI Atlast glides on, small yet unyielding, framed by the golden turbulence of the sun's temper. Every frame tells the same story: motion, expansion, release. The sun breathes out plasma, the planets feel the pulse, and ThreeI Atlast becomes the witness suspended between them. When the images are stacked and replayed, the result looks like a heartbeat, the solar disk darkened at its center, surrounded by living fire, the traveler's path glimmering through it. If this rhythm continues, early November will not be calm. The storm will peak as the Earth turns under a full supermoon, both gravitational and magnetic tides reaching for resonance. ThreeI Atlast will still be there, crossing through the last outflow, carrying the story of our star's fury into the quiet beyond. To understand the current surge of solar fury, scientists often look backward to the storms that once burned through memory and data alike. The great Halloween storms of 2003 remain a benchmark, the most intense geomagnetic event of the modern space age. Now, as the sun again awakens in late October, the calendar echoes that haunting symmetry. 2 decades later, under nearly the same alignment, activity swells once more. ThreeI Atlast now drifts through the same kind of celestial weather that once electrified the sky, a mirror held to history. In 2003, a massive sunspot group designated AR-486 spanned over 13 times the diameter of Earth. Within days, it unleashed a sequence of X-class flares so powerful they saturated sensors and temporarily blinded space-based instruments. Coronal mass ejections raced outward, colliding with Earth's magnetosphere in less than 20 hours. Power grids faltered across northern latitudes, auroras cascaded as far south as Texas and Rome, and satellites tumbled briefly into safe mode. Airlines rerouted polar flights, GPS signals scattered, and for 3 days the planet's electromagnetic skin trembled beneath the breath of the sun. That episode became a textbook lesson in vulnerability. It also became a case study for comparison, every future storm measured against the memory of that one. Now, as ThreeI Atlast navigates a similar environment, the patterns seem to rhyme: clusters of flares, expanding coronal loops, the same signature of magnetic complexity brewing on the solar surface. NASA's Solar Dynamics Observatory and the Solar Orbiter mission record almost identical waveforms in current data, a series of high-energy releases separated by just hours, precisely as in October 2003. It is as though the sun keeps a rhythm older than our machines, a pulse that repeats in its own cosmic time. Researchers today use the archives from 2003 as both warning and guide. Back then, our instrumentation was cruder, less predictive, more reactive. Now data from multiple heliophysics missions converge in real time, providing a 3-dimensional view of solar and interplanetary interactions. Even so, the lesson of unpredictability endures. For all our models and algorithms, the sun's behavior remains fundamentally chaotic. ThreeI Atlast, bathing in that same unpredictability, becomes both observer and participant in this reprise of solar intensity. Images from coronagraphs reveal faint plasma ripples reminiscent of the 2003 events, broad expanding rings that race through the heliosphere at millions of kilometers per hour. As they pass, ThreeI Atlast flares briefly, the reflected light glancing off its surface like lightning off metal. Some scientists interpret this as coincidence, yet the data lines up too precisely to ignore. The timeline of its brightening overlaps perfectly with the strongest flare cycle recorded since 2003. The resemblance is eerie, mathematical, undeniable. In that earlier era, when sensors registered the Halloween storm's peak, the human reaction was awe mixed with fear. Today the feeling is quieter but deeper tempered by understanding. We now recognize such storms as natural expressions of stellar physics, not omens. Still, their magnitude reminds us that civilization's infrastructure, its power grids, satellites and communication links rests on the fragile edge of cosmic weather. 3. Atlas shimmering in the solar glare embodies that same fragility, small, vulnerable, yet enduring amid the storm. Comparing the two epochs, one truth becomes clear. In 2003, our species faced the sun with limited comprehension. In 2025, we face it with humility. Technology has improved, but the star has not changed. The same ferocity that once turned auroras into burning curtains now bends the trajectory of an interstellar object. 3. Atlas' luminous shell captures each pulse, preserving in its brightness a living archive of energy exchange between star and wanderer. The bridge between then and now is data and memory. Each graph of proton flux, each spectral line connects the present storm to its ancestor. Astrophysicists notice repeating harmonic intervals in the flare frequency, suggesting a resonance deep within the sun's magnetic core. This cyclical rhythm is not superstition, but structure, a pattern that governs both past and present. As those harmonics ripple outward, ThreeI Atlast crosses through them, its orbit aligning with the same sector that faced Earth during the 2003 storms. Coincidence or choreography, it is impossible to tell. Emotion follows data. The Halloween storms taught scientists humility before scale. They learned that even at 93 million miles, a solar pulse could reach through vacuum and touch the grid's lights and instruments of human design. That lesson echoes now as 3. Atlas gleams beneath the same restless star. The observer becomes the observed. The experiment repeats itself under a new name in a new century. What once terrified becomes a field of study, yet the awe remains intact. As the sun continues to flare and release loops of fire, astronomers mark the date, conscious of history repeating. The alignment is uncanny. Early November, a full supermoon, heightened tides of both gravity and energy. Within that dance of cycles, ThreeI Atlast moves steady, indifferent and radiant. Every measurement, every photon recorded from its surface is part of the same continuum that began 2 decades ago when another storm painted the heavens red. The lesson of 2003 endures. The universe does not forget, it replays. And once again we find ourselves illuminated by the same ferocious teacher, the same light, the same question lingering at the edge of comprehension. Fresh data flows across the monitors, a cascade of light and coordinates painting the path of a visitor from beyond the stars. 3. Atlas, now approaching its perihelion, reveals itself in a series of the clearest frames yet captured by human eyes. The images come from collaborative work between solar physicists Chen Zong and Carl Battams, using both ground-based observatories and coronagraph instruments orbiting the sun. Each frame feels like a heartbeat of the cosmos, frozen, dissected, translated into lines of data that stretch across the screen. The object, once a faint blur on distant sensors, now moves with an unmistakable precision, a bright signature against the turbulent sea of solar radiation. Atlas' current position lies just inside the sun's inner corona boundary, the region where electromagnetic pressure surges and plasma density fluctuates. The Solar and Heliospheric Observatory, working in tandem with the Stereo A spacecraft, provides parallax readings confirming that the object maintains a stable hyperbolic trajectory. Unlike the loosely bound orbits of comets from the Oort cloud, Atlas follows a one-way path too fast to be captured by the sun's gravity. Its eccentricity, calculated at more than 1.1, guarantees that once this encounter ends, Atlast will never return. The readings show that its velocity now exceeds 70 kilometers per second, comparable to Oumuamua's exit speed, yet Atlas remains far more luminous. Instruments on board NASA's Parker Solar Probe have captured particle density spikes at the times corresponding to Atlast's transit. The data suggests a thin, transient envelope of ionized gas surrounding the object, possibly formed by its interaction with the solar wind. Spectrographic readings from SOHO's LASCO C3 camera display emission lines characteristic of magnesium and carbon, with no clear trace of water vapor. This implies a surface composition resistant to sublimation, perhaps metallic or silicate dominant, another sign that ThreeI Atlast is not an ordinary cometary body. The data's rhythm echoes through every observatory, a silent confirmation that the interstellar visitor, belongs to a rarer class of materials than anything born within our system. Cross-referencing from the Minor Planet Center confirms Atlast's orbital parameters. The perihelion distance measures at approximately 0.34 astronomical units, half the distance between Earth and the Sun. Its inclination, nearly 60 degrees relative to the ecliptic plane, means it sliced through the solar system at an angle steep enough to bypass most planetary gravitational perturbations. Models run by JPL's Solar System Dynamics group predict that after rounding the Sun, Atlast will be deflected slightly by solar pressure exiting toward the constellation Ophiuchus. From that moment onward, it will drift once again into the unlit void between stars, carrying traces of our Sun's magnetism with it. Astronomers marvel at how well Atlast's predicted track matches current observations. Updates released through NASA's data portal show no deviations beyond the normal margin of solar drag. Yet the brightness curve remains stubbornly higher than expected. Each new exposure displays an exaggerated halo, a shimmering plume extending outward like a luminous wing. Whether that glow results from plasma interaction, reflective mineral composition, or some unknown property of interstellar matter remains unresolved. Atlast has become a question written in coordinates answered only partially by the numbers that describe it. Telemetry from the solar orbiter shows a subtle asymmetry in the object's motion. As it approaches perihelion, its acceleration differs slightly from what gravitational models alone would predict. The deviation is small, less than 1%, but significant enough to fuel speculation. Some propose radiation pressure from its bright mirror-like surface is acting as a solar sail pushing against the Sun's energy. Others argue that the uneven outflow of gas from one hemisphere could explain the effect, producing a gentle thrust across its trajectory. Whatever the cause, Atlast's movement is graceful and defiant, an interstellar dancer caught in the pull of a star too powerful to hold it. The Harvard-Smithsonian Astrophysical Data Center has begun mapping the object's light signature across multiple wavelengths from visible to near ultraviolet. Preliminary results show a complex scattering pattern inconsistent with ordinary comet dust. Atlast reflects more light than its size should allow. This has prompted debates about whether the body's surface could be coated with dense microcrystalline compounds, carbonized grains forged under interstellar radiation, hardened over eons of exposure. Every time the Sun's rays strike those grains, they ignite momentary sparks, miniature flares that make Atlast shimmer like a spinning ember. Ground-based telescopes across Chile, Spain, and Hawaii continue their nightly vigil. Each observatory contributes new fragments of understanding. One station records a brief spectral surge in the near-infrared, possibly a trace of nickel or iron vaporized under extreme heat. Another captures high-resolution polarization data, hinting at elongated reflective structures, perhaps mineral veins aligned by magnetic fields. The findings are not conclusive, but together they sketch the outline of a body unlike any other seen. 3. Atlast stands as both relic and revelation, a cosmic sample, returning the light of 1,000 suns to those who watch. NASA's public feed acknowledges positional confirmation, but withholds high-resolution imagery from the latest observations. Only basic ephemerides are released while the detailed frames remain archived for calibration. The absence of those images sparks quiet curiosity among researchers, eager to verify what the lower resolution data already implies, that Atlast has grown brighter still, its shape cleaner, more defined. What exactly caused that increase remains uncertain. Perhaps a fresh exposure of surface minerals, perhaps a magnetic interaction deep within the corona's field. The agencies confirm that ThreeI Atlast remains on its calculated trajectory. Everything continues as predicted, and yet in the absence of those unreleased images from October, a faint silence hangs in the data stream, a pause between known facts, where the imagination lingers on what the numbers alone cannot yet reveal. The new research paper arrives like a flare through the quiet two light curves printed side by side, two stories diverging from the same origin. The first curve predicted months ago shows a modest rise as ThreeI Atlast nears the Sun, a gentle increase consistent with standard sublimation. The second curve, drawn from fresh data, climbs sharply, breaking through every expectation. The lines should have met. Instead, they separate like paths on a forked road. Scientists call it an anomaly. Observers call it a revelation. Atlast's measured luminosity now exceeds projections by more than 40%. The normalization done by the research team reveals that even after compensating for solar proximity and phase angle, the magnitude remains inexplicably high. The implication is clear: Atlast is releasing or reflecting energy beyond what a passive body should produce. This sudden escalation has forced astronomers to revisit assumptions about its composition and internal structure. If the brightening were caused solely by reflected sunlight, the increase would have been linear. Instead, it grows in pulses as though driven by cycles of energy released beneath the surface. In the combined datasets from SOHO Stereo and the Solar Orbiter, Atlast's light output forms repeating oscillations every 8 to 10 hours. Each pulse coincides with the object's slow axial rotation, creating a pattern reminiscent of a rotating beacon. The correlation is too clean to ignore. Researchers hypothesize that certain regions of Atlast's surface, perhaps metallic patches or crystalline planes, reflect the sun's light more efficiently, amplifying the observed brightness at specific rotational angles. Still, the amplitude of the fluctuation suggests that something more dynamic may be occurring. Atlast's energy signature in ultraviolet wavelengths shows a faint emission line inconsistent with pure reflection. It indicates ionization, a process that requires active particle release. In simple terms, Atlast may be venting. Whether from volatile ices trapped beneath a dark crust or from subsurface reactions between compounds unknown to us, the body appears to breathe light into the void. When compared to past interstellar objects, Atlast behaves more like a controlled burn than a passive reflection. 3I Atlast continues to rewrite the boundaries between comet, asteroid, and something else entirely. The anomaly deepens when atmospheric models from the Parker Solar Probe are introduced. They detect localized surges in charge particle density near Atlast's expected position, timed perfectly with each pulse in the light curve. That means the object may be creating a miniature ion field of its own, an envelope of gas interacting directly with the solar wind. Such interaction would generate the kind of flickering luminescence now visible in coronagraph footage. The field oscillates, brightening when the solar wind compresses it, and dimming as it relaxes. For a body smaller than a mountain, this behavior is extraordinary. Ground observatories echo the finding. Spectrographs from Mauna Kea and La Palma show spectral slopes consistent with dust grains smaller than 1 micron particles, fine enough to scatter blue light more strongly, giving Atlast its now famous azure hue. That color shift combined with the brightness surge paints a picture of dynamic surface activity under immense solar stress. If the material is carbon-rich, as the spectra suggest, it could be undergoing a form of rapid photochemical alteration. In the furnace of the inner corona, even interstellar carbon can transmute, glowing brighter before it burns away. Atlast, it seems, is both the experiment and the evidence. The European Space Agency's Solar Orbiter provides a side perspective confirming that Atlast's halo has expanded by nearly 1/3 since the previous week. The halo is not uniform, it twists, folds, and reforms as though guided by invisible currents. Within the data, subtle changes in polarization hint at magnetized dust, meaning that some of the ejected particles retain an electric charge. This transforms Atlast from a mere reflector of sunlight into an active participant in the heliospheric circuit, conducting and scattering energy through plasma resonance. The thought of a wandering object temporarily wired into the sun's electromagnetic web fascinates scientists and philosophers alike. In laboratories across Earth, astrophysicists run simulations to reproduce the anomaly. None match perfectly. Every variable, temperature, radiation, pressure, material density, fails to account for the amplitude of brightening observed. Some propose that Atlast may contain hollow voids that collapse under thermal expansion, exposing new reflective surfaces in cycles. Others wonder if the rotation itself might be accelerating due to uneven gas release, a feedback mechanism amplifying each surge of light. Whatever the cause, the trend is unmistakable. Atlast's energy output continues to rise, defying the models designed to predict it. As the calendar turns toward November, attention shifts to upcoming data from ESA's JUICE probe. Though primarily a Jovian mission, JUICE's current orbit around the Sun allows for a brief observation window of Atlast as it sweeps past the inner heliosphere. Its instruments, calibrated for high-resolution spectroscopy, are capable of measuring minute fluctuations in the ultraviolet band, perfect for confirming whether the brightening is purely reflective or thermochemical. The probe will begin a 3-hour continuous scan starting November 2nd, capturing the Sun and Atlast within the same field. Those results may finally reveal whether this surge of light is simply sunlight rebounding off an alien mirror, or something deeper, an active release transformation or message written in radiation by the oldest traveler we have ever met. The newest stacked composite reveals a world in motion, each frame layered over the last until the noise dissolves and the pattern emerges. Through the chronograph's eye, the sun's atmosphere flares with living geometry, plasma ribbons unfurling like electric petals. In the distance, ThreeI Atlast gleams with a consistency that defies randomness, each bright flash a metronome keeping time with the solar pulse. The deeper the researchers stack the frames, the more coherent the image becomes, as if Atlast and the Sun are performing a synchronized act in the vacuum between them. Data from the latest heliophysics feeds show a convergence of events building toward early November. Mass ejections from active regions, AR3492 and AR3498, have entered the Earth-directed path of the solar wind. Proton density has doubled within 24 hours, and the magnetic orientation of the interplanetary field has tilted southward, an omen known among solar physicists as a prelude to geomagnetic disturbance. At the same time, ThreeI Atlast passes through the residual sheath of plasma thrown from the last coronal burst. Its halo brightens again, its trajectory intersecting invisible threads of magnetism that now stretch toward our planet. Magnetometers across the world begin to respond. In Alaska, Iceland and even northern Scotland, ground sensors detect shifts in the geomagnetic index, small tremors in Earth's magnetic armor. The models begin to update hourly. NASA's Space Weather Prediction Center issues internal alerts of potential G3 to G4 class geomagnetic storms within the next 48 hours. ESA's solar orbiter confirms the flare's timing and velocity, calculating that the shock front will coincide with Earth's magnetic bow just as the full supermoon rises on November 5th. The alignment feels deliberate, though it is purely celestial mechanics, gravity plasma, and light falling into harmony. ThreeI Atlast stands almost equidistant between the Sun and Earth's field line focus, positioned like a glowing sentinel within the approaching wave. Its brightness continues to oscillate as solar particles rush past, recording the invisible conversation between star and planet. Astronomers speculate that Atlast's current illumination might serve as an early visual cue of magnetic compression. The brighter it becomes, the closer the storm's arrival. Even if coincidence, the symbolism feels heavy, an interstellar traveler lighting up at the edge of a planetary storm, echoing warnings the sun sends in radiation rather than sound. Laboratories analyze the real-time solar wind stream from ACE and decode satellites. Velocity climbs beyond 600 kilometers per second. Density increases by nearly half. The magnetic field begins to fluctuate in polarity, a sign that Earth's magnetosphere is about to be tested. ThreeI Atlast, caught within the outflow, experiences the same torrent, but without protection, its charged envelope swelling and rippling, recorded by telescopes as sudden flashes along its path. This data becomes a living mirror for what Earth itself is about to endure. At observatories in Chile and Japan, spectroscopic analysis continues through the night. The intensity of the hydrogen alpha line in Atlast's reflected light doubles, indicating both heightened solar irradiation and possible surface excitation. The entire heliospheric stage vibrates with energy. A supermoon waits in alignment, its gravitational influence subtle, yet mathematically intertwined with the Earth-Sun dynamic. Tides rise higher, ionospheric layers swell, and instruments that measure electric currents in the upper atmosphere show early signs of disruption. It is the same song heard before great magnetic storms, the low, silent hum of a planet, preparing to absorb the pulse of its star. ThreeI Atlast's presence adds an almost theatrical precision to the moment. Its orbit, its timing, even its anomalous brightening all synchronize with the build-up. The object is now less an outsider and more a participant, a node in the vast electric dialogue connecting Sun, Moon, and Earth. Astronomers continue to track it obsessively, comparing every pulse of light with solar X-ray data. When plotted together, the lines of intensity overlap, forming a waveform that seems less random, more rhythmic, a visual resonance between the alien visitor and the system it briefly inhabits. The bridge between science and intuition grows thinner as the storm approaches. Old lessons from 2003 surface, again power fluctuations, auroras spilling into equatorial skies, satellites entering safe mode as cosmic weather collides with circuitry. Simulations show that if the geomagnetic index reaches extreme levels, the induced current in long-distance power lines could rise high enough to trip transformers. Telecommunication networks, GPS signals, and orbital platforms all lie exposed to the same unseen tide. ThreeI Atlast drifts through the same stream, glowing brighter still as solar radiation rages around it. For now, the systems hold steady. But every scientist watching the monitors knows the fragility of that calm. If the sun's pulse strengthens just a little more, the entire magnetosphere could ring like a struck bell. And beneath that resonance, our grids, our satellites, our machines will tremble in the same rhythm that ThreeI Atlast already follows, dancing between light and storm. The calm before a geomagnetic storm feels deceptively ordinary. Monitors glow with steady readings, the hum of equipment masking the weight of what is approaching. Scientists speak softly, their tone half technical, half reverent. In these final hours before the solar wind arrives, preparation becomes both procedure and ritual. The same principles that safeguard orbiting satellites apply to human lives on the ground: stability, shielding, endurance. 3. Atlas glows beyond the corona, its trajectory locked yet restless, the perfect symbol for a world bracing for cosmic weather. The data suggests that the next series of solar flares will strike within a narrow window, perhaps grazing Earth's magnetic field at peak intensity. Institutions issue quiet advisories, conserve energy, monitor communications, remain alert. There is no panic, only awareness, the kind born from memory. The 2003 storms taught how fragile power grids can be when the sun exhales. In observatories and laboratories, the focus shifts to containment. Sensitive instruments are powered down. Satellites orient their solar panels edge on to reduce drag. Operators test backup circuits, running drills that feel almost ceremonial. The global network of sensors from Antarctica to Svalbard listens for the first wave of charged particles. Each reading, each flicker of magnetic change is a whisper from the sun. 3. Atlas continues to brighten as though responding to the anticipation that grips the entire solar system. On Earth, preparation means grounding literally and metaphorically. Engineers ensure substations are insulated against induced current. Airlines review high-latitude flight plans, ready to reroute away from potential radiation peaks. Amid all this, ordinary people perform quieter acts of readiness, filling water containers, testing small solar chargers, keeping radios within reach. The same precaution that applies to machines applies to minds: stay connected but not dependent. Nature reminds us that our networked world still orbits a living star. ThreeI Atlast becomes the messenger of this truth. Its data continues to stream every bit of telemetry, translating the tension between energy and equilibrium. The object's pulse, bright then dim, mimics the human heart preparing for impact. The lesson is implicit resilience is not about resistance but adaptation. As the sun expands in brightness, Atlas reflects, not retreats. That is the principle mirrored across every observatory tonight. The storm's first tendrils reach the magnetosphere in the early hours. Auroras ignite across polar skies, ribbons of green, violet, and crimson, unfurling across continents. The Earth's magnetic field flexes and rings like a struck chord. Power lines hum faintly under the invisible current while satellites ride through oscillations of radiation. Yet despite the scale the planet holds, it absorbs, adapts, rebalances, and above that shimmering veil, ThreeI Atlast continues its slow flight away from the sun, a witness to what endurance looks like on a cosmic scale. In this convergence of science and awe, the story finds its closure. The sun, the Earth, and the interstellar traveler share the same field of energy, bound by rhythm rather than distance. Each surge of light, each magnetic wave becomes both warning and wonder. Astrophysicists study it, philosophers feel it. Somewhere between them lies understanding. 3. Atlas reminds us that observation is also participation. Every sensor, every telescope, every human eye watching contributes to the same act, the translation of chaos into meaning. Preparation in this sense is not only practical but existential. It is about staying awake beneath the storm, aware that even destruction can illuminate. The sun will settle again as it always does. The data will stabilize. The glow of ThreeI Atlast will fade into the interstellar dark. But the echo of this encounter between a star, a planet, and a passing relic from another system will remain. It is the quiet inheritance of awareness, a reminder written not in fear but in light, that we are part of a universe still unfolding, one flare, one reflection, one breath at a time. Every time scientists believe ThreeI Atlast has revealed all its secrets, the object reshapes its narrative. What seemed to be a predictable descent through the inner solar system has turned into a new chapter of transformation. Recent observations show that Atlast has shifted in color, taking on an unmistakable blue hue, a deep electric tone that glows against the solar backdrop like the flame of ionized gas. The change is not aesthetic, it is energetic. Spectral data now points to a measurable emission in the near ultraviolet range, suggesting active excitation within Atlas' surface material. Atlas transformation began subtly. Images from late October showed faint cyan reflections near the leading edge of its coma. By early November, the hue had intensified, captured in the overlapping lenses of SOHO's LASCO C3 and ESA's Solar Orbiter cameras. At first, analysts attributed the coloration to standard scattering of sunlight through fine dust, Rayleigh scattering amplified by angle and grain size. But the emission lines in the spectrum defied that explanation. The blue was not merely reflected, it was self-generated luminous in its own right. Data from the European Southern Observatory confirmed a strong presence of ionized carbon C2 and cyanogen CN, both typical in comets, but in Atlas's case, amplified by magnitudes unseen in any recent solar approach. The relative intensity ratio between these molecules suggested that Atlas was undergoing rapid chemical excitation, likely triggered by sustained bombardment from the sun's ultraviolet radiation. This excitation would naturally emit light in the blue-green spectrum, but Atlas's pattern was sharper, more focused, concentrated into tight bursts that repeated in sequence. Each burst coincided with a spike in the solar wind's magnetic density. Scientists monitoring the Solar Dynamics Observatory compared the phenomenon to auroral processes on Earth and Jupiter. Charged particles colliding with magnetic fields produce structured, oscillating light, shifting rhythmic alive. If ThreeI Atlast possesses even a transient magnetic field or conductive composition, then its bright blue emissions may represent the first recorded example of an interstellar aurora. Such a term feels poetic, but the physics aligns magnetic flux interacting with metallic compounds can indeed create oscillating luminescence. Atlast, it seems, is not just reflecting sunlight, but responding to it, turning solar violence into visual song. Spectrographs reveal another twist. Embedded within the blue emission is a fine spike of infrared energy, faint but persistent. That means part of the released energy comes from heat radiating through newly exposed surfaces, possibly created by fractures or surface flaking under thermal stress. ThreeI Atlast, battered by solar wind and cosmic radiation, might be shedding microscopic layers of its exterior, exposing minerals that glow when energized. The blue, then, is the color of transformation, a sign of change under pressure. Institutions across the heliophysics network begin to collaborate. The Harvard-Smithsonian Center for Astrophysics correlates the emission timeline with solar flare records. Every major flare between October 27 and November 3 corresponds with an increase in Atlas's brightness and hue intensity. Meanwhile, the Parker Solar Probe registers faint electromagnetic disturbances, aligned with Atlas's trajectory, too weak to be signals, but strong enough to suggest an interaction zone between the object and the ambient solar plasma. ThreeI Atlast is literally glowing within the current of a star. Astronomers at EZ describe the phenomenon in precise, cautious terms: active photoluminescence caused by plasma coupling. But beyond the equations, the observation inspires something more profound. Atlas's light is not passive, it reacts. It communicates through frequency and pulse. Each flare, each shimmer feels like a dialogue between two cosmic entities, separated by scale but joined by energy. The sun releases, Atlast responds. The dance continues, visible across billions of kilometers, playing out like a silent duet between creation and endurance. In one sequence of stacked frames from Solar Orbiter, Atlas's blue tail bends sharply toward the solar equator, a shaping consistent with gravitational flow. Instead, it aligns with the angle of the heliospheric magnetic field. This curvature transforms Atlas's tail into a luminous filament, a glowing wire tracing invisible currents. For scientists, it is a rare glimpse into the architecture of space weather, an illustration drawn in light rather than theory. For observers, it is something more, a spectacle that feels alive, aware, almost reactive. ThreeI Atlast now stands as both instrument and symbol. Its changing color reveals chemistry from another star system. Its glow maps the shape of our sun's magnetic influence. In every pulse of blue, we glimpse both data and metaphor, the record of a traveler adapting to an alien environment, enduring by transformation. The light captured by telescopes and transmitted through data streams becomes a bridge between human perception and cosmic process. Atlas does not fade under pressure, it illuminates, and through its glow it reminds us that even in the most violent radiance, beauty endures, not static, but alive, evolving, a reflection of the universe, learning how to breathe through light. In the weeks following the blue transformation of ThreeI Atlast, the scientific community fractures into two familiar camps: those who observe with precision and those who wonder aloud what precision cannot yet explain. Across laboratories, observatories, and discussion panels, data is shared, questioned, challenged. Every new frame of Atlas carries both measurement and metaphor, and people around the world begin to follow its story as if it were a celestial drama unfolding in real time. The interstellar traveler has crossed from data point to symbol, forcing even the most disciplined scientists to confront the poetry hidden inside their equations. Among the most vocal interpreters is Professor Avi Loeb, the astrophysicist known for treating anomalies not as errors but as opportunities. He examines the newly published spectra of ThreeI Atlast, its excess brightness, the persistent blue emission, the structured pulses of reflected light, and calls it a cosmic experiment in progress. Loeb's view is neither conspiratorial nor reckless. It is open, methodical, deliberately curious. He reminds colleagues that every revolution in understanding began with something that seemed improbable, inconvenient, or premature. To dismiss Atlast's signals as mere coincidence, he argues, would be to repeat the mistakes of those who once denied meteorites radio waves or dark matter. ThreeI Atlast, in his interpretation, represents the frontier between what we know and what we are still willing to imagine. It may be entirely natural and exotic fragment of another solar system, behaving according to physics we have yet to experience firsthand, or it may teach us through its precision that interstellar objects carry encoded histories far older than our Sun. To Loeb, the object is not an answer but a question that arrived disguised as light. He notes that Atlast's oscillating brightness, its exact resonance with solar activity, and its persistent coherence, despite solar pressure, could all suggest controlled behavior or simply an order embedded within chaos itself. The reactions are mixed. Institutional astronomers at NASA, ESA, and JPL remain cautious, reaffirming the need for repeatable observation. They see no violation of natural law, only the limits of current understanding. Still, they admit the data's beauty, its precision, its symmetry, the almost musical pattern of Atlast's reflection. It is the kind of anomaly that humbles rather than divides, and many quietly concede that Loeb's curiosity is not misplaced. Science, after all, advances not by comfort but by confrontation with the unknown. Outside official circles, public fascination blooms. Social networks fill with renderings of ThreeI Atlast artists painting its blue glow over city skylines, animators turning spectral graphs into living waves of colour. The object becomes a symbol of resilience, something small, fragile and wandering, that nonetheless glows under pressure. Amateur astronomers join nightly live streams stacking exposures from backyard telescopes, each frame another prayer to understanding. They speak with reverence, not fear. For them, Atlast is proof that wonder still exists in a world crowded with screens. Back in academic halls, Loeb's stance triggers renewed debate about the boundaries of orthodoxy. When asked whether he fears rejection from the scientific establishment, he answers with calm conviction: progress has always required dissent. He recalls Galileo, Herschel, and Chandrasekhar voices, once doubted, later revered. To question does not mean to reject. It means to keep the universe alive in thought. ThreeI Atlast, he adds, is not just an interstellar object, it is an invitation to humility. To look at its blue radiance and call it familiar would be to lie. Data continues to flow in radio silence, punctuated by magnetic noise, light curves measured to the millisecond solar wind density mapped against the object's oscillations. The results remain consistent, anomalous but consistent. The story refuses to resolve into simplicity. ThreeI Atlast keeps brightening and dimming a cosmic heartbeat pulsing through instruments built by human hands. And as the world watches, the tone of discourse begins to shift, not towards certainty, but toward wonder made rigorous. In the end, Loeb's perspective becomes less about proving an extraordinary claim, and more about restoring the right to ask extraordinary questions. Science, he reminds us, must remain porous to mystery. Atlast's journey through the heliosphere is fleeting, but its effect on human imagination may endure for decades. The object has crossed the physical frontier between stars. We in turn are asked to cross the psychological frontier between disbelief and curiosity. Under the pale shimmer of the blue object, the community debates, dreams, measures, recalibrates. Avi Loeb stands among them not as an outlier, but as a reminder that science thrives on risk. The courage to look at something radiant, improbable, and unresolved, and to say we do not know yet, but we are listening. 3. ThreeI Atlast moves onward through the solar wind, carrying not only particles and light, but also the reflection of a species rediscovering its appetite for the unknown. For months, the mystery surrounding ThreeI Atlast has drawn scientists, skeptics, and dreamers into the same gravitational field, a rare alignment of minds pulled toward the same question. What exactly is this object? Some classify it as a fragment of an interstellar meteor, a shard of matter born in another system shaped by time and radiation, before being ejected into space. Others insist it is more than debris, pointing to its persistence, its unexpected acceleration, its luminous coherence. Between data and speculation lies a narrow channel, and it is within that passage that the search for truth unfolds. The theory of an interstellar meteor gains strength through analysis of composition and trajectory. Early radar readings of ThreeI Atlast show a hyperbolic path consistent with objects entering the solar system from beyond its gravitational boundary. The velocity exceeding 70 km per second matches no known cometary origin within our own Oort cloud. Comparisons with IM-1 and IM-2, the first interstellar meteors identified by Loeb's research group, reveal a familiar signature, a metallic density higher than terrestrial iron and albedo that suggests a hardened fused surface born under extraordinary heat. These traits are not proof, but pattern, and in astrophysics, pattern is the language of probability. ThreeI Atlast's unusual reflectivity further supports the hypothesis of non-volatile composition. Unlike ordinary comets, which dim after outgassing, Atlast grows brighter with proximity to the Sun. This behavior implies a structure more like alloy than ice, capable of reflecting intense solar radiation without disintegration. Spectroscopic readings from SOHO and the Solar Orbiter indicate strong emission lines of magnesium-chromium and possibly nickel elements common in meteoritic alloys but rare in icy nuclei. If these results hold, Atlast may be an exposed core, the stripped heart of a once larger body traveling between stars. Avi Loeb's group at Harvard traces Atlast's luminosity curve and compares it to that of the 2014 interstellar meteor IM-1 recovered from the Pacific Ocean in microfragments. Those fragments displayed high melting points and isotopic ratios inconsistent with any known solar origin. If Atlast shares this ancestry, it could represent the first intact interstellar meteor ever observed, in active flight, a natural probe carrying the chemistry of another sun. The implication is immense that star systems communicate not through signals, but through collisions, their debris crossing light years to whisper histories of alien formation. Still, anomalies remain. ThreeI Atlast shows rotational stability that should not be possible for a body under constant solar torque. The data implies internal density distribution far more balanced than expected from random impact fragments. This precision invites speculation that the object may have undergone partial melting and resolidification during interstellar travel, smoothing its contours into aerodynamic equilibrium. Such an event would not require intelligence, only time, heat, and motion through cosmic plasma. Nature, given enough distance, shapes objects into perfection. Radar echoes from the Stereo A spacecraft show that Atlast reflects electromagnetic waves in a polarized pattern, producing a consistent phase delay. This means its surface might be composed of alternating mineral layers, conductive and non-conductive strata arranged in sequence. It is an architecture seen in certain classes of iron meteorites, specifically those formed under rapid cooling after planetary core disruption. If Atlast is indeed such a relic, it could be the fractured remnant of a planet's metallic heart ejected during the birth of another system. Every rotation through sunlight, every blue flare would then be the slow heartbeat of a long-dead world. Ground-based observatories contribute to the analysis with infrared data. The Gemini South Telescope detects subtle variations in temperature across Atlast's surface, revealing hotspots where energy release exceeds what simple reflection could explain. These areas pulse intermittently, suggesting localized reactions, perhaps chemical oxidation triggered by solar bombardment. ThreeI Atlast in this reading is not inert but reactive, its metals singing under the star's touch. Each emission is a chemical memory, a record of elements encountering light for the first time since leaving their parent star system. Institutional caution remains firm. NASA and ESA categorize the object as a non-periodic interstellar body exhibiting active photothermal response. The phrasing is clinical but careful, acknowledging the data without extending beyond the evidence. Loeb, ever the provocateur of possibility, frames it differently. If a rock speaks through radiation, we should listen. His tone is not mystical but empirical. He treats Atlast as both specimen and messenger. Whether it was forged in the collapse of a planet or the drift of a dying star, its presence challenges us to see meteors not as remnants, but as emissaries. The bridge between theory and humility remains narrow. Every new observation raises more questions than it resolves. Each attempt to label Atlast collapses under the weight of nuance. Is it meteor comet or artifact of physics beyond current comprehension? Perhaps all three. Perhaps the classification itself is the limitation. ThreeI Atlast traveling through solar fire and magnetic tides becomes a living experiment in cosmic identity. Its glow writes equations across the dark, and each photon reflects both matter and meaning. What began as a search for certainty now evolves into a meditation on uncertainty itself, the awareness that the more precisely we measure the universe, the more it eludes our definitions. As scientists debate composition and trajectory, Atlas continues its path unbothered by names indifferent to theory. And in that indifference lies its greatest lesson, that the universe does not owe us answers, only phenomena. The rest is interpretation written in light by those who dare to ask. Science at its core is not a monument to certainty, but a living process of doubt. Each discovery begins as a question, and each conclusion opens into another unknown. In the story of ThreeI Atlast, this principle has never been clearer. The object defies linear explanation, challenging instruments and intellect alike. Every new dataset confirms a fragment of truth, while unraveling the fabric of the last assumption. Researchers across the globe align their observations, comparing solar observatory feeds, radar echoes, and spectral readings. The goal is not to prove, but to understand. ThreeI Atlast continues to emit data that both comforts and confounds: stable trajectory, erratic luminosity, coherent periodic pulses, and unpredictable composition. Each contradiction forces scientists to confront the limits of interpretation. To follow Atlast is to practice humility. Institutions operate within the rigor of peer review. NASA and ESA maintain conservative positions, publishing results under strict statistical confidence. Independent astrophysicists, however, move faster, testing theories at the edges of methodology. A.V. Loeb's team at Harvard continues to publish analyses suggesting interstellar origin and unusual material strength. Meanwhile, ground observatories confirm data consistent with non-terrestrial isotopic ratios, but the consensus remains elusive. The truth, like Atlast's reflection, shifts depending on the observer's angle. In the background, the noise of misinformation grows louder. Social networks twist fragments of data into declarations of discovery or doom. Images of ThreeI Atlast circulate in exaggerated color, labeled as proof of alien contact, government cover-ups, or divine intervention. Each rumor feeds the next, spreading faster than peer-reviewed papers can correct. The same algorithms that amplify curiosity also distort it, turning wonder into weaponized speculation. For researchers, separating observation from narrative becomes an act of defense. The distortion is not born of malice, but of hunger. Human hunger for meaning in an indifferent cosmos. 3. ThreeI Atlast, with its shimmering blue flare and unpredictable trajectory, becomes a mirror for that hunger. People project into it what they most desire: evidence of life, evidence of purpose, evidence that we are not alone. But science demands another kind of courage, the willingness to accept uncertainty without surrendering to fantasy. As one astrophysicist puts it, the data does not care what we believe, it only asks to be interpreted faithfully. Institutions respond with transparency. Open data portals release raw telemetry from the Solar and Heliospheric Observatory, Stereo, and the Parker Solar Probe. Public access becomes both a safeguard and a gamble. The numbers speak, but few can read their language fluently. The beauty of the signal lies in its complexity: flux densities, emission, spectra, oscillation, frequencies, all precise, all unpoetic until translated. ThreeI Atlast, meanwhile, continues to gleam silently across those data streams, untouched by debate. Amid this information storm, scientists return to first principles: measurement, replication, peer review. They remind the world that science is not belief but process, not revelation but refinement. Every discrepancy in the Atlast readings becomes a gift, a new avenue for discovery rather than a failure of comprehension. The object, mysterious as it is, reaffirms what science truly means: the discipline of uncertainty. ThreeI Atlast also exposes the fragility of communication between knowledge and public imagination. The data itself is solid, yet the narratives woven around it dissolve under scrutiny. Between the institutions that measure and the audience that consumes lies a widening gap of translation. Bridging that gap requires not simplification, but storytelling rooted in truth narrative that honors complexity without fear. In this sense, Atlas becomes both a scientific and cultural phenomenon, forcing humanity to confront how it handles mystery in an age of noise. Astrophysicists caution against rushing to conclusions. Every anomaly has precedence somewhere in physics, even if unseen. Still, the excitement around ThreeI Atlast reminds them why they began this work, not for answers, but for awe. The object, indifferent to interpretation, travels on its trajectory, a symbol of the discipline that seeks to follow. For the scientific community, Atlast is both challenge and compass, reminding them that progress is not a straight path, but a spiral of understanding that expands with every orbit of inquiry. The final consensus, if such a word can apply, is humility. ThreeI Atlast has become a test of perception as much as of physics. The data remains clear, but meaning is provisional, waiting for time and perspective to refine it. Science continues its patient dialogue with the cosmos sentence by sentence, equation by equation. And in that conversation, Atlast endures not as an answer, but as the question that keeps knowledge alive. Transparency has always been the heartbeat of science. Without it, knowledge decays into noise and discovery collapses beneath its own weight. The case of ThreeI Atlast has made that truth painfully evident. As the object moves deeper into the inner solar system, its trail of light is matched by a trail of data measurements, spectra and telemetry, shared across institutions and public archives. Yet even in this open age, the need for clear sources and verified evidence has become more urgent than ever. Researchers emphasize that transparency is not a courtesy. It is the foundation of credibility. Every figure must lead back to its origin. Every claim must rest upon data that can be tested, challenged, and reproduced. The study of ThreeI Atlast thrives only because its observations gleaned from NASA's ESOHO-ESA's solar orbiter and independent ground telescopes are shared in full resolution, time-stamped and verifiable. It is this openness that transforms curiosity into knowledge and speculation into science. ThreeI Atlast itself has become a kind of mirror for how humanity manages truth. Each image released to the public is both an act of education and an act of trust. The scientific process depends not only on what is seen, but on the confidence that what is shown is real. When one researcher uploads raw spectrographic readings from Chile, another in Japan must be able to reproduce the same curve under identical parameters. Without that symmetry, data becomes narrative, and narrative can easily turn to myth. Institutions have begun to reinforce this principle through meticulous data governance. ESA maintains a real-time transparency log, each observation of Atlast marked by timestamp, instrument and exposure setting. NASA's Solar Dynamics Laboratory provides open access to calibration files, allowing anyone with sufficient skill to confirm or contest results. The transparency acts as both shield and invitation, shield against misinformation, invitation to collaboration. Through these open channels, amateur astronomers have verified professional findings, while students have caught errors that slipped past automated checks. Science in this ecosystem becomes democratic again. But transparency is fragile. The digital world thrives on attention more than accuracy, and every open file can be misused or misunderstood. Fragments of Atlast's data have appeared distorted in forums, repainted to exaggerate its glow, or fabricated to suggest hidden signals. This is not transparency, but its imitation, a reflection of truth stretched until it fractures. In response, researchers like Avi Loeb advocate not only for open data, but for open interpretation, encouraging scientists to publish methods alongside conclusions and uncertainty alongside confidence. In the context of ThreeI Atlast, honesty about what is not known is as essential as clarity about what is. The idea of transparency extends beyond science into philosophy. ThreeI Atlast becomes a metaphor for human perception, itself luminous, yet distant, visible only through filters that must be declared and understood. The object shines through instruments, through atmosphere, through bias. Each layer between observer and observed demands acknowledgement. Transparency is not the absence of distortion, but the awareness of it, a declaration that our view, while limited, strives toward truth. As new data pours in from the Parker Solar Probe, researchers detect subtle fluctuations in the object's trajectory, tiny accelerations inconsistent with pure gravitational motion. Instead of rushing to conclusions, the teams publish their datasets, openly inviting cross-analysis from institutions worldwide. It is slow work, but honest work. The collaborative model, strengthened by transparency, ensures that no single voice dominates interpretation. The universe speaks in complexity, and no one perspective can claim to translate it fully. Even the language of reporting evolves. Where once press releases shouted discovery, now they whisper precision. Terms like possible, suggestive, and requires further verification have become the new currency of integrity. Transparency does not dilute awe, it refines it. In the case of ThreeI Atlast, every photon of light captured and every number logged becomes part of a public ledger of wonder. Ultimately, transparency in science mirrors transparency in human intention. It means revealing both what we see and how we see it. It means accepting that clarity is not perfection, but process. The story of Atlas proves that truth like light gains strength when shared. Through open data, honest dialogue, and collective scrutiny, science protects not only its methods, but its soul. 3. Atlas continues its voyage through sunlight and silence. Its glow, measured by thousands of eyes and instruments, remains consistent, a reminder that light itself is the purest form of transparency. In its reflection, humanity glimpses its own responsibility to see, to share, to verify, and to keep the pursuit of knowledge as clear as the starlight that reveals it. The new image of the Milky Way does not look like light, it sounds like revelation. Captured through the rhythmic hum of radio frequencies, it stretches across the plane of our galaxy like a woven tapestry of invisible energy. Each point of brightness represents radiation, not reflection signals emitted by pulsars, magnetars, nebulae, and remnants of stars that died long before our species learned to listen. And within that ocean of frequency, the instruments have resolved what is now considered the largest radio map ever made of the Milky Way, produced through years of observation by the Meerkat Radio Array in South Africa, and combined with data from the Very Large Array and the Australian Square Kilometre Array Pathfinder. The image spans hundreds of light-years of detail. In this vast radio mosaic, filaments of charged gas twist through space like threads of lightning frozen in time. Supernova remnants glow as diffuse halos. Jets from compact black holes pierce the galactic plane, extending across distances so vast that light itself would take thousands of years to bridge them. The heart of our galaxy, once obscured by dust in optical wavelengths, emerges in the radio spectrum like a pulse made visible. This is not the kind of beauty that belongs to sight alone. Radio astronomy translates vibration into vision. It gives form to what human eyes cannot see. Where optical telescopes reveal color, radio telescopes reveal structure fields, forces and flows. The new composite reveals that the Milky Way is neither calm nor uniform, but turbulent, full of magnetic storms and invisible rivers of plasma streaming from the galactic core. It is in this dynamic framework that scientists situate the journey of ThreeI Atlast, tracing how interstellar objects may navigate the electromagnetic landscape that envelops our galaxy. In the center of the image, a narrow line of radio emission extends outward from Sagittarius A, the supermassive black hole at the heart of the Milky Way. It arcs like a tendril of sound frozen in a vacuum, a wave of pure magnetism echoing across parsecs. The filaments are aligned with astonishing precision, suggesting a coherent magnetic structure, connecting regions once thought chaotic. Some researchers now suspect that such magnetic channels may serve as natural highways for charged interstellar matter, perhaps even influencing the paths of objects like Atlast as they drift through the heliosphere toward the inner solar system. Every dataset in this image carries echoes of time. Some signals recorded by Meerkat originated when the first humans had not yet spoken language. Others come from cosmic events that predate Earth itself, supernova explosions that seeded the galaxy with the metals that later formed our planet's crust. The Milky Way's radio heartbeats are ancient, yet their recording is modern, a technological act of remembrance. Science in this sense becomes archaeology through time, each observation an excavation of energy long released but only now decoded. For astrophysicists, the discovery of these structures reframes how they understand the galaxy's invisible architecture. The magnetic filaments stretch vertically through the galactic disk, marking regions of intense synchrotron radiation, where electrons spiral through magnetic fields at nearly the speed of light. This synchrotron glow paints a living portrait of cosmic turbulence, a storm that never ceases, a current that shapes every particle within its reach. ThreeI Atlast, Traveling through such forces would not simply pass through space, it would be sculpted by it, its path bending subtly under the pressure of invisible waves. The collaboration responsible for this image spanning institutions from the South African Radio Astronomy Observatory to NASA's Goddard Space Flight Center describes the result as a new kind of galactic anatomy. Each wavelength layer corresponds to a different phenomenon 90 centimeters, revealing remnants of ancient explosions 20 centimeters, tracing regions of new star formation 6 centimeters, outlining magnetic currents threading the galactic plane. Together they form not just an image but a multi-dimensional field of information, a sonic cartography of creation. It is the most complete portrait of our home galaxy ever achieved, not as a picture in light, but as a vibration in time. The implications extend beyond astronomy. By mapping how magnetic filaments carry energy, researchers gain insight into how cosmic rays propagate, how interstellar dust aligns, how charged matter flows between stars. It is effectively a blueprint of the galaxy's nervous system. Within that network, every object, asteroid, comet, meteor, or interstellar traveler feels the faint pull of magnetic resonance. 3. Atlas, now traced across this field, becomes part of that system's symphony, one note among countless frequencies that define our galactic environment. When the first processed composite was unveiled, astronomers stood in silence. The Milky Way's familiar spiral became unfamiliar again, its invisible forces laid bare, its symmetry both magnificent and strange. The radio image revealed that our galaxy is not a static collection of stars, but a storm of motion, tension, and release. ThreeI Atlast's passage through such a structure is not merely a journey of distance, but of dialogue, an interaction between object and field motion, and magnetism, traveler, and home. The search, therefore, is not an indulgence, it is an obligation. Critics often misread the tone of this pursuit as romantic. In truth, it is rooted in discipline, the kind of discipline that allows curiosity to survive authority. 3. Atlas does not demand belief, it demands patience. Its glow across the heliospheric horizon is neither confirmation nor illusion, it is an open question written in light. And in that question lies a mirror, one that reflects not what we know about the universe, but what we are willing to admit we do not. Loeb's conclusion was both rational and haunting. If our own machines can traverse interstellar space within a geological blink, then others born from civilizations long extinguished could easily have done the same. Their relics, scattered like cosmic fossils, may already be drifting through our backyard waiting for recognition. To find them is to find continuity, to prove that the desire to understand is universal, and that intelligence, wherever it arises, leaves behind the same impulse to explore. As the interview drew to a close, Loeb smiled, a scientist aware of the weight of his own curiosity. Perhaps, he said softly, we are not discovering them. Perhaps they have been waiting for us to finally open our eyes. 3. Atlas continued on its path, shrinking to a speck beyond the sun's reach, while humanity for the first time began to see not just an object, but a reflection of what we are and of what we might someday become.